All right, so today I just wanted to talk a little bit about just the basics of what we can do with a quantum channel and quantum cryptography. Cryptography in a digital age is paramount. Being able to send securely stuff that other people have access to, from secure documents to passwords to state secrets to, you know, a text message. You just want things to be secure. So we'll just go through a little bit of how cryptography is developed up until now, and what quantum computers can do for cryptography in the future. So the basics of cryptography start with this. We have two agents. We're going to call them Alice and Bob. That's just what they're called standardly. And then we have some eavesdropper. And the eavesdropper has access to the information that's sent across a public channel. And we want to make sure that we can communicate between Alice and Bob without the eavesdropper Eve getting involved. Okay. And so there are a bunch of ways to do this. The simplest, the most basic method is what we call symmetric key encryption. So I have a message, and I'm going to encode it into some what we call cipher text. There's a specific rule set out for me, and I'm going to say, all right, this letter maps to this letter, and this letter maps to this letter, and I jumble up the letters until it doesn't make any sense to read. But at the very least, you know, when I send the message, Bob on the other end knows what I did and knows how to therefore undo the scrambling. And so we say that Alice encrypts the message, sends the message to Bob, and Bob can decrypt the message. And the process by which we encrypt the message and decrypt the message are symmetric. They're the inverses of each other, and they're the same process. Okay, and so the way this works is if Alice and Bob agree ahead of time on a way to encrypt and decrypt the messages. Okay, so as long as Eve doesn't know how they've encrypted the message, the eavesdropper can't be involved. So a very crude, one of the oldest forms of cryptography out there is called Caesar's cipher, and it's just a very basic symmetric encryption procedure. And what they do is you take each letter and you go a certain number of digits of units down in the alphabet list. And so every letter is translated the same amount of units to a different letter in the alphabet, 26 of them in total. And that's the scheme. So as long as we don't know which way it was, it would be slightly difficult to calculate. And so this was used commonly for military messengers and things. You could encode a message. Somebody picks up the message. They have no idea what it says, and they have no idea how to decode it. They've never heard of this cipher before. And so for all practical purposes, it was useful. But of course, this is very crude. If you knew how the cipher was created, all you'd have to do is try 26 possibilities, 26 different ways to decode the message, and one of them would likely make sense. So Caesar cipher wasn't going to really work. But what if we made it a lot more difficult for Eve to decrypt the message? What if there were a lot more? Oh, before we go there, a little warm-up exercise for everyone. So we have a cipher where each letter, when we encrypt it, is shifted two units to the right. Okay, this is a very basic process, Caesar cipher. So if we have our letter A in the message, it's going to be encrypted to C in our cipher. And if we have our letter B in the message, it's going to be encrypted to D in the ciphertext. So a little practice, decrypt this message and It's a little bit tedious, but it's kind of fun. Gets everybody's brains going. Yep. Wow, that was quick. That was very quick. Yep, that's what it says. Yep, I love quantum. Did I get an R in there? Is that going? Yeah. So I like, yeah. If you guys were smart and did the first letter and then tried to guess, that's definitely the way to do it, hangman style. Okay, so what if we made this process a little more complicated? So we know how the thing is encoded. We know how the thing is decoded. And if Alice and Bob both know this process, we just want to make it hard for Eve to guess what the decryption process is. In the encryption, so yes. So Ashley brings up a good point. Is it to the right or to the left? It's to the right to encode the message. So we shift it to the right to encode, and then to get back to the original message, we have to go to the left. Yeah. Great. Okay. So Enigma was used by the Germans in World War II. If you all have seen the movie The Imitation Game, with it's about Alan Turing and the computer they built. It's an incredible movie. You should totally watch it if you haven't seen it already. But they went over how they cracked the Enigma encoding machine, and Enigma was just another example of a very complicated symmetric encryption scheme where we had some text and we'd type a letter into the machine, and then it would automatically be mapped through a complicated series of routings to a light board, and then we'd know what letter we should put in our ciphertext. Okay, so it was very complicated. Pretty much nobody would want to calculate all these things by hand. It was all done digitally. But to know how the encryption process worked, you had to know the position of these wheels. So these wheels had different mappings depending on the input and the output. They jumbled things together in a very specific way. And in order to decrypt messages, you need to know how it was encoded. You need to know the position of these wheels. So if you change the position of the wheels, you get a totally different answer, and you would be able to decrypt the message properly. So the problem becomes for Eve, how do I figure out how to decode a message? Well, now instead of just having to try 26 different possibilities, I have to try millions or thousands or hundreds of thousands. Either way, before digital computers, this was an entirely impossible problem to solve. And so if you'll remember what they did in the movie, if you saw the movie, was that they built a computer. The Allies built a computer to solve all these possibilities at once and figure out. And they used some tricks to narrow down the number of possibilities and stuff. But the idea was so many different possibilities, it's much harder to figure out how the decryption scheme works. But the weakness was this: once you figured out, once you were into the system, then it was pretty easy to stay in the system, because if you're the Germans and you have messaging stations all over the place and you're sending messages over the airwaves, you have to communicate anytime you want to change the position of the wheels. Anytime you want to change the way the encryption scheme is done, and this was another layer of security, if they changed the position of the wheels all the time, even if you figured out how to break the code for one day, you'd only be able to decode the messages for a day, and after that, we'd have issues. So the point is, they had to communicate the key to encrypting and decrypting messages publicly. They had to use the encryption decryption process to change the key itself. So if you're already in, you could figure out how they were going to change the key for the next day, and then you were pretty much fine. And then you could decrypt all the messages indefinitely. So that's a weakness of the system. And we see that this weakness doesn't come apart with what we use now in the modern world is what we call asymmetric encryption. So we want to know how we can communicate how to change the position of these wheels. And a lot of times if you change the encryption key, if you make the encryption key communication completely secure, if you're telling all of the other Enigma operators how to change the position of the wheels securely, then it still becomes very difficult for you to break in. There are ways to make even symmetric encryption. Symmetric encryption, you can use it only once and make it prohibitively difficult to break. Okay, so that brings us to public key encryption, and how this works is Alice and Bob will each have a private key. They'll choose a private number. We'll call Alice's private key A and Bob's private key B. And so Alice and Bob are never going to communicate A and B directly over a public channel. Okay, so these are going to be private numbers to themselves. Bob will not know Alice's private key, and Alice will not know Bob's private key. Okay, they're private. Okay, unlike in symmetric protocols where the key to encoding the message, Alice and Bob both had to know it. Now with this public key, this asymmetric encryption, we don't need that. Okay, so we're also going to, Alice and Bob will agree publicly on two prime numbers, G and Q, okay? And these prime numbers are going to be useful, you'll see in a second. And then we'll assume that our eavesdropper Eve has access to these numbers because they're communicating on a public channel. Public channel meaning everything they say could be heard by Eve. Okay, so what we're trying to do again is for Alice and Bob to share some information that Eve can't know. That's the goal of the whole thing. And so what makes this different from symmetric key encryption? We'll see. So this is one example of how this process works. And all of the variants of, or I should say most, I'm not positive that there are other variants out there that don't use this process, but we're using the modulus of an exponential function. So we take the letters G and Q, the variables that we decided on earlier, they're prime numbers, and if we raise G to the power of some number, X, and then take the modulus with respect to Q, we'll have some number, and that's what we're going to communicate publicly, okay? And we'll see why we do this in a second. But can you envision what the modulus function looks like? Have we heard of that before? Do you know what the modulus function is? Yeah. Yep, so the percent sign in Python is percent sign. Yeah, it's the remainder. So modulus 2 is always going to be either 0 or 1, right? Modulus 3, then you can have 0, 1, 2, and exactly, it's the remainder. Great. So as you can imagine, there are many possibilities. If you have the result of this function, say Q is a number 23, there are 22 or 23 possible numbers, but the ways of getting those 23 possible numbers are infinite. There are so many different ways to get the outcome 0 or 1 or 2. Okay, so here's how this works. Alice sends Bob she's going to take her private key and calculate this function x with her private key. So g to the a modulus q. Okay, and then Alice is going to send that to Bob. Okay, and then Bob is going to do the same thing. Bob's going to send Alice x of b, which he created using his private key. Okay, so at this point, Bob and Alice have sent something using their private key, but they have not communicated their private key directly. Okay, and so now what's going to happen is Alice is going to receive the message from Bob that has x of b, and Alice is going to compute x of b to the a. She's going to take the answer she got from Bob and raise it to the power of her private key. And Bob is going to do the same thing. Bob's going to take the answer he received from Alice and compute that answer to the power of his private key. Okay, so now we have these values here. And what's cool about this whole process is that now Alice and Bob share a secret value S. The secret value S is equal to x of a to the b, and it's also equal to x of b to the a. And so what's cool about how this process works is that these two numbers are equivalents. And here we show a little bit how that works. X of b to the a is g to the b modulus q to the eighth power, which is the same thing as g to the a b modulus q, which is the same thing as g to the ba. Okay. So does that make sense? Yeah, so we're assuming the messages are just numbers. Yes, we could, as we saw in module 2, there are many, many ways to map all kinds of information to bits, right? So in this case, we're using numbers, which are themselves encoded in bits, and those numbers can also be mapped to specific kinds of information. So if you remember the image that we wanted to send, or we didn't want to send it back then, in module 2, we were just talking about how we represent an image as a series of numbers. We represented an image as a series, as a 2x2 grid of pixels, and each pixel had 3 numbers associated with it, and that was the combination of red, blue, and green in the pixel. Okay, and those 3 numbers were enough to encode what computers understand as a meaning, as what color to reproduce in the image. So we can convert letters, numbers, images, all kinds of data, anything we want, we could represent it with bits. So just because we're using numbers here doesn't mean that it only works for numbers. We can just encode all of our information in numbers. And as long as the number stuff anything we send across the channel, no matter what we do to it on the front or back end, as long as the number version is secure, as long as we can't get the encoded version, we can't get the decoded version. Okay, and we have no reason to encrypt the mappings. Mapping a color to a number, we don't have any reason to encrypt that. As long as the numbers we send are secure, our process is still protected. Does that answer your question?
Yes, can I ask another?
Sure.
So, okay, so I was just trying to like work through an example of the math, and it was like, okay, so if Alice's key A is equal to 2 and Bob's key B is equal to 3, and we say, well, the function x of, let's see, Alice is she's going to know what x of 3 is, and I'm going to just say that the function is equal to whatever the key value is, just to be simple. So Alice knows 3, and she computes 3 to 3 squared, so she computes a 9. Bob knows A, which is 2, and he's going to 2 to the 3rd, which is only 8, so they're not equal.
Right. They're not equal, but when you take the modulus, they should be.
But we didn't do the modulus till later. Or no, wait a minute, hang on. Can you show us a very simple mathematical example?
Yeah, you know, so yes. What I'm worried about though is I'm going to mess this up. The general idea was to give you maybe we can come back to that at the end, because the general idea was just to give you a schematic of how this asymmetric process works.
Yeah, but the numbers don't mean anything.
the variables. So the key to, okay, so we have another question here. Is the equation at step 5 always true? Yes. Yes. The equation at step 5 is always true. And that's the brilliance of the whole thing, is we haven't, what makes this asymmetric is that we haven't tried to undo this function. And we'll see in a second that this is very computationally difficult to go backwards, but it's very easy to go forwards. So to create x of a and x of b does not require a lot of computational power, but to undo it requires an extensive amount of computational power. Okay. It's possible, you all are right, it's possible there is something going on here that I've missed. Generally speaking, for now, let's just say we can trust that it works, and I can come back to it or send you all something to assuage your curiosity, which, yes, okay, there's a link. Great, so let's just talk about possible intervention strategies. What could happen if Eve wanted to get a hold of this information? So Eve's our eavesdropper, and Eve could figure out what was going on with either A or B. Okay, if you could calculate the secret value, then Eve could calculate the secret value. So how could you get your hands on A or B? Eve knows x of A. Eve knows x of A because x of A was sent on a public channel. So the question would be, why can't we just solve the equation g to the A mod q? Because remember, Eve also knows g and q. It turns out that this equation is very difficult to solve backwards. It's very difficult to solve backwards, and it's impossible even on the strongest classical computers. The strongest classical computers, it's very difficult to work backwards and figure out what this A is. Okay, if you know x of A and you know it should be equal to g to the A mod q, it's still very difficult to find what A is. Okay, and that's how we remain secure. Not that it's not possible to calculate this A, but that it's not practical. It would take an infinite amount of time on classical computers. They could do it, but it would take way too much time. So for all practical purposes, we're entirely secure for now. So what's the point of going quantum at all then if we have this secure protocol? Well, Shor's algorithm, which Kanav talked about yesterday and gave you an introduction to, can solve this equation, g to the A mod q, in a reasonable time. So unlike classical computers, a quantum computer can solve this problem a lot faster. And what that does is that questions the security of our current asymmetric encryption protocol. We rely on the fact that it's impossible to, or very, very difficult to computationally solve this mod q equation. And now that now that we can solve it, all our encryption protocols could break down. All you need is a quantum computer, and then you're able to access all the information that's communicated across channels. Okay, so the good news for us is that quantum computers aren't ready to do this. We don't have to worry about our encryption schemes breaking down anytime soon. Quantum computers aren't capable of implementing Shor's algorithm yet. Okay, but hopefully we can expect that by the time quantum computers can implement Shor's algorithm, we have an alternative, which is this new security protocol based on quantum computers. Okay, so let's get to that now. Let's talk about the process for quantum key distribution. Okay, so here's what's going to happen. We have a photon, a qubit. We're going to send that photon in one of 4 possible states. And what we can say is that we're just encoding a single classical bit. So we want to send the bit 0 or 1, for instance. We want to send the bit 0 or 1, and we're going to encode it in one of 2 bases. Okay, we have the standard basis, or the computational basis, and that corresponds to the states 0 and 1. And then we have the Hadamard basis, which corresponds to the plus state and the minus state. Okay, so 4 possibilities. And you've seen these states before. You've seen the plus state, you've seen the minus state, you've seen 0 and 1. Bob is going to receive this qubit. Okay. Yes. 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 Bob is going to receive this qubit in measure in either the Hadamard basis or the standard basis. Hadamard basis or standard basis. And there are 2 possibilities. So Alice encodes in a random basis, either the standard basis or the Hadamard basis, and Bob measures in a random basis, either the standard or the Hadamard. So there are 2 possibilities here. If Alice and Bob use the same bases to decode the bit, then Bob will measure the correct bit 100% of the time. Okay. If Alice encodes 0 and Bob measures in the standard basis, there's no issue. With 100% probability, Bob will measure 0. But if Alice and Bob measure in different bases, then Bob is only going to get the bit that Alice had intended about 50% of the time, not about, roughly 50% of the time. So before we go on, I thought we'd just take a look at a few examples to see how this works. So suppose we wanted to send the bit 0, and Alice is going to use the standard basis. So that corresponds to the state 0. Now Bob could either measure in the standard basis, which means Bob would measure 0. Okay. But if Bob chose to measure in the Hadamard basis, that would be equivalent to asking, is the state plus or minus? Okay. And so what we could do is to show, actually, before I go on, is it clear that if I were to measure in the Hadamard basis, I would have a 50% chance of getting 0 and 1? The plus and minus? Yeah. Yeah. Good. Good. So then we don't need to go over that. essentially what you'd do is you'd rewrite the 0 state. You'd rewrite the 0 state in terms of plus and minus, and you'd see that there's an equal superposition of plus and minus. So when you measured it, you would get plus half the time, which corresponds in the Hadamard basis to a 0, and half the time you get a 1, which corresponds to minus in the Hadamard basis. Okay, so we could do this for all the possibilities, but if they choose the same basis, they're going to have the bit correct all the time. If they choose different bases, they're going to have different bits. And so Alice and Bob are going to do this a bunch. They're going to measure, they're going to encode a bit in random basis, measure in random basis. And then after the fact, they've done all this, they know which measurements correspond, and now they can talk publicly. They're not going to bother hiding this conversation from Eve. They're going to say, when did you use which basis? So Alice and Bob are going to go through. I used the Hadamard basis on the first one. Oh, me too. I used the Hadamard basis. Good. That means we can keep that bit. Okay. And then if Alice says, I used the standard basis, Bob's going to say, oh, darn, I used the Hadamard basis. Okay. That's a bit we're just going to throw out. Don't worry about it. We're not going to keep the information because you only have a 50% chance, Bob, of knowing the bit that I was trying to send you. Okay. So we're going to go through and we're going to throw out all of the possibilities where we didn't use the same basis. Okay. So that's it. And now Alice and Bob have a list of bits that they both know. And that could be used as a key for a symmetric encryption scheme. It could be used as a key for other kinds of protocols. But the point is, now Alice and Bob have information that only they know. Okay. And that was the goal all along. So before we can just go on and prove that this method is an absolute success, let's take a look at what Eve could possibly do to interfere in this situation. Okay. So Eve doesn't know, like Bob, Eve doesn't know which basis Alice used to encode the bit. Okay. Eve doesn't know. And the only way for Eve to find out is by making a measurement. Okay. Eve has to measure the state to figure out what state it's in as an attempt to gain some information about what's happening. So Eve's going to make a measurement in a random basis. Eve's going to make a measurement in a random basis because, again, Eve has no idea. So about half the time, Eve's going to guess the wrong basis. Does that make sense? Just like Bob guessing wrong about half the time, Eve will guess wrong half the time because Eve has no idea. And there are only two possibilities, so you get it right half the time. But what happens is if Eve gets it wrong, she's going to collapse the state that Alice was trying to send into a different basis state. So let's go back to the Jamboard and talk about what that means. So we have Eve, Alice, and then Eve, and then Bob. Alice was trying to send the state to 0. So Alice is trying to send the state plus, which is 0 plus 1. Eve guesses wrong. Eve is going to measure in the standard basis, which means 50% of the time, Eve is going to measure 0, and 50% of the time, Eve is going to measure 1. So now, depending on what Eve measures, the state is either 0 or 1. Not plus. Okay. So if Eve hadn't interfered, and say Bob chose also to measure in the Hadamard basis, Bob chose to measure in the Hadamard basis, then if not for Eve, Bob would have gotten the bit 0, measuring the plus state, every time, 100%. But with Eve involved, Bob's going to measure in the Hadamard basis, and either 0 or 1, Bob's going to have a 50% chance of measuring the bit 0 or 1. And so not only has Eve not obtained any useful information, Eve has also messed up the communication between Alice and Bob. Bob now has the wrong bit. So if Bob and Alice were to go back and say, oh, you used that Hadamard basis, I used the Hadamard basis, great, so we can keep that bit. But now Bob had a chance of getting the bit wrong because there's a 50% chance that Bob measured wrong because Bob didn't know that Eve interfered. And we're saying, oh no, that's a really effective way for Eve to get involved. Eve could just keep measuring things and totally screwing up. And yes, Eve could do that. And you might think of that as a really bad thing, but that's actually a fundamental feature of what makes this process so secure, is that Eve's interference in the whole process hasn't messed Alice and Bob up. What Eve has done is made her presence known. Now, Alice and Bob can detect when Eve is getting involved in their business. All Alice and Bob have to do is every once in a while you check a few bits. You say, what did you get for this bit? What did you get for this bit? Okay, so we measured the same basis. Let's check our bits to make sure no one's interfering. And if they're interfering, then we'll know something's up. Okay, so yeah. So Alice and Bob can check a few bits, and they can check if someone's snooping. And they'll be able to know someone's snooping because Bob will get the wrong answers sometimes. And if Bob's getting the wrong answers, they'll know that somebody else is measuring the state before it gets to Bob. And so in this way, we can detect Eve, which makes this protocol secure. It doesn't mean that Eve couldn't get involved, but Alice and Bob at least would know about it. Yeah, so what if Eve entangled her qubit with Alice's qubit? Would she have the answer for every bit? Wouldn't she have the answer for every bit at the time Bob measures? So there's only one qubit involved here. There's only one qubit involved. So Alice takes the qubit, takes a photon, and sends it to Bob. And so I guess that leads us to possibly a second way. If Eve had another qubit, what if Eve made a copy of the state? Eve made a copy of the qubit on her own qubit, kept that state, and then just waited for Alice and Bob to tell what bases they used. And if they use the same basis, that's good, because now Eve can just measure the copy on the same basis. Eve can measure the copy on the same basis, and then Eve would have the information just like Bob, and Bob and Alice would never know the difference. But fortunately, for quantum computing, there is the no cloning theorem, which guarantees that Eve can't copy the state. So if Eve can't copy the state, then there'd be no way to delay measurement. Eve either has to measure, and that's the only possibility. And so that concludes our description of quantum key distribution. There are all these bits now that Alice and Bob know that Eve doesn't know, and that's the purpose again. Regardless of eavesdropping, how do A and B guarantee fidelity in the info they send if they're losing random bits? Yeah, so there's an element of hardware and noise that's going to get involved. Is that kind of what you're asking? Yeah. So we can do this process a large number of times, and there are classical error correction techniques. So you could send specific bits in certain orders, and I think that might be a little beyond the scope of what we're talking about now, but there are error correction techniques to make up for this in the long run. If I send the bit string 0, 0, 1, 0, 1, and one of the bits got messed up, there are ways for Bob to know, okay, I can tell there's a bit messed up here because something was supposed to be true of these 5 bits as a unit, and I'll be able to correct it. And so in the case of low fidelity, there are ways to correct for the errors. If you have a large number of bits, if you do this a bunch, there are ways to make up for that. Yeah. So yes, there's a whole class of error correction, which is quantum error correction. Absolutely. In this case, yes. What we were talking about yesterday with quantum teleportation, that is a way to send quantum information. But this is a bit more primitive. This is just sending a classical bit. Yes, Michael, that's a good question. So why Eve's interference would alter the bits? Why Alice's measurement wouldn't do the same? In other words, why do we assume that the interference of Eve is going to mess up the bits? Yeah. Okay. Good. Let's go over that in a little bit more detail. Did I miss any questions earlier on? Okay. So let's go back to the Jamboard a little bit. So this is rare. The detectability of Eve is relatively rare because if Eve 50% of the time gets the same basis as Alice, they guess the same basis, because Eve has no idea what basis Alice used. So Alice picks a random basis, and if Eve does the same, that's about half the time. Then the state that Eve measures, say Alice wants to send the 0 state, and Eve measures in the standard basis as well, then the state is still 0. We haven't collapsed the state, or rather we have collapsed the state, but to whatever it already was. We haven't modified this state in any way, right? But if Alice wants to send the plus state, Eve measures, is this state 0 or 1? But before, it was in a superposition of 0 plus 1. So when Eve measures, the state is going to collapse to either 0 or 1. But it's no longer in this plus state. Eve has affected the measurement by collapsing the state. Is that good so far? We see how Eve has changed the state by measuring it? Because that's the key to the whole thing, that the measurement collapses the state into one of the basis states. And then, if the state is either 0 or 1, and Bob measures in the correct basis that Alice had intended, the Hadamard basis, which is also rare, right? The fact that, first of all, the chances of Alice and Eve getting the same basis are 50%, and the chances of Alice and Bob getting the same basis are 50%. But what we need is for Eve to get the wrong basis and Bob to get the right basis for us to be able to detect it. That's the only condition unless this works, in which this works. And that's going to happen only 25% of the time. So only a quarter of the time we're going to be able to detect, to even check whether Eve was snooping, okay? But that's okay because we only have to check a few number of bits. If Eve's snooping, Eve is snooping. And Eve, presumably, if Eve knows some quantum mechanics, Eve isn't even going to bother trying. because Eve knows that there's no way to do this, and that's kind of what's great about the whole setup. But suppose Eve does try futilely to be able to gain information. Eve's not going to know which ones to measure or not, and even if 1 in 100 bits came up wrong, or 1 in 100 error-corrected bits, if we're thinking about, you know, we've done 1,000 bits, and then we've error-corrected, and so we only have 10 valid bits, 1 in 100 is wrong, we'll know something is up. So, did I answer the question? Great. Awesome. So yes, I'm not prepared enough to explain how the asymmetric key description works, but we can write something up and send it. We can do it in office hours and clear that up. But just know that Shor's algorithm is a problem for those classical asymmetric key algorithms, and that's that. So yeah, to recap, Shor's algorithm can defeat asymmetric cryptographic protocols, and quantum key distribution is provably secure. So I think that's it for now, barring any other questions.
Great stuff, Eric. I guess
Great.
I think there might be some other stuff that you can do to increase that 25% number as well. So like even a higher ratio. But Eric's, you know, the principle is definitely true. If there's no way for Eve to guarantee her success in attempting to eavesdrop, there's no way to 100% of the time know. Yeah, great stuff.
Eve could totally get lucky.
Yeah. But the point is that on aggregate, you know, right, you will get caught very quickly. Yeah, exactly. Yeah. And so that's the power. That's what provably secure means, right? Yeah, right.
Yes. It's not that Eve can't get 1 bit correct, but knowing 1 bit is totally useless in the grand scheme of things. Information, what we consider meaningful information, is communicated in thousands and millions of bits.
Yeah.
So.
And as the number of bits increase, the probability that an eavesdropper can get lucky and receive all the information goes all the way down to 0. Like eventually it becomes guaranteed. With 0% probability, you will succeed.